Hi, Dr. Cook here, and today we're going to be talking about the effects of wind. Okay, so let's start our discussion of wind effects with what kinds are there. All right, we can start out with the idea of a crosswind, which is wind that acts along the z-axis, so things coming laterally from the sides. All right, we also have what we call a range wind, which is wind along the x-axis. Okay, remember that our positive direction is going downrange. All right, so things that are going in the direction that we're shooting is our range wind. All right. Now, in these analyses, we're going to make some assumptions. All right. So we are going to assume that our velocity that our projectile is traveling at is much greater than any of our wind velocities. Okay. We're not dealing with a super slow projectile where the wind might actually be moving faster. All right. So this works good for like our rifle bullets and our artillery. Right. We're going to be assuming a point mass, all right, for our model here, and that we're dealing with flat fire. All right, so the following sets of equations are based on those kind of low angles. This isn't going to work for mortars or high angle artillery. We're also going to assume that wind in the y direction coming up from the ground or some kind of downdraft is roughly 0. And we're going to be ignoring that, right? So we only have this crosswind or range wind to worry about. And we're going to be assuming a constant air density. That goes along with kind of our flat fire assumption, but that over the range that we're shooting at, we're not dealing with something where air density suddenly changes at different positions. All right, so how do we model wind? All right. If we start out with an equation here, kind of looking at a point mass, right? We start from that, and we've got these velocity terms there, right? So this deals with both the scalar velocity and the velocity vector, and then we've just got gravity and our drag, right? This is our simple model here, and if we want to introduce wind, then we're going to have to add a term in here to get our wind in. All right, so what we do is we make a difference in the wind, right? So the wind is going to be subtracted out of the velocity of the projectile to get a relative velocity, and our scalar is going to, we're going to put this tilde over it, and that v tilde is just the absolute value of that difference with the wind velocity. Okay, and this is because what we really care about with the aerodynamics is the velocity of the projectile relative to the air that it's in and not relative to the ground, all right, which is what V is. All right, and then we're going to introduce this C hat starred sub D for a coefficient here. So we've got like a little hat and a star on the coefficient. Just a way to capture that those constants of the air density and our reference area S and the mass of the projectile to carry that through and simplify our algebra later. That's 9.70. So if we want to look at our velocity change with respect to time, all right, in all of the x, y, and z directions, we can rewrite those out in this manner. All right. Now gravity is only acting in the y direction. All right, so the other two don't have a gravity term in them, but we're just introducing this v tilde and our wind being subtracted out of our vector velocity. All right, so let's introduce our flat fire approximation into the situation here. And what we're going to do is rederive our equations using those flat fire assumptions. The first important step here is to realize that our v tilde is approximately equal to the Vx minus the wind x. All right, they're within about 1% of each other. All right, so we can say that they're roughly the same. All right. So then we can rewrite our equations here for x, y, and z, our changes in velocity or accelerations. All right, by making that substitution for our v tilde. All right. Now, you'll note that in the x direction, we could rewrite that with, instead of the two parentheses, they're the same. We could put a squared term on there, right? So Vx minus Wx squared would be the same thing. And then we have all of these equations. Now, The vertical wind, Vy, if there was any, acts like a crosswind. All right, it kind of has that same kind of behavior. It's going across our symmetrical projectile. All right. Now, usually it is very small, and we are going to go back to that assumption that our wind in the y direction is approximately 0, which means that we could just cancel that term out if we wanted to. All right, so we could write the algebra in some different ways to express our equations here. These are 9.115, 16, and 17. Let's look at the case of a constant crosswind, so steady wind coming in from the sides. All right, this is going to cause a lag in our time of flight compared to our vacuum trajectory. All right, it's going to slow things down a little bit. First, we can calculate then a lag time. All right, which is t lag is equal to a t minus x over Vx naught, right? Our range divided by the muzzle velocity in the x direction. Important concept here is what we call the lag rule, all right, which tells us that z equals the wind in the z direction multiplied by that lag time. That's equation 9.132. And what we've got here is z is how much wind deflection we're going to get. How much is the crosswind going to make our projectile go off target to the side? All right. Now this x over the Vx naught is our vacuum time of flight. All right. In a vacuum trajectory, how long would it take to get there? All right. And then our t term here is our actual time of flight. Okay. Once we consider in the drag. And all of that in the parentheses is that t lag, which here we're showing immediately above us. Now let's look at the situation for a variable crosswind. Okay, so if as we go down range, we're going to encounter different crosswinds with different velocities at different places. This can happen. This is realistic, especially when we're shooting at, say, 300 meters, right? There's differences in terrain. There might be a hill blocking the wind in one spot or a group of trees, and then in another spot we've got more wide open and the wind is blowing through. Or if we're shooting at really long distances, 1, 2, 3 kilometers, right? We could obviously have some very different wind conditions at different locations as we move down range. So we have to be able to analyze that, all right? Now, so we have this equation 9.133 that our change in the z direction is equal to that wind times the change in the time minus a change in x divided by that velocity naught in the x direction, right? This is coming out of that lag rule from above. We've just changed some deltas in, or put some deltas into there, right? And if we expand that out, what we get is these z sub i's. Now these i's are time steps. We'll talk a little more about that in a second, all right, or locations, all right? And we're looking at what happens over these discrete intervals, right? You'll notice these are all intervals. So the way to solve this is we're going to treat it piecewise, all right? We're going to take little discrete segments of our flight, our trajectory as we move down range. We're going to tabulate things like t, vx, x, and then we're going to be able to calculate the z, or the delta z for each step. All right, so that looks something like this. We're going to lay out a table. All right, so in time interval 1, so we start out at I0, right, and then we're going to go to I1. So we've got an interval from 0 to 1. And we already know our initial conditions, right? So when we start out at I equals 0, our x position is 0, our velocity is just the muzzle velocity. Wind will be whatever's given to us at the start. Time is 0, and our deflection is 0, right? But then we're going to start filling in the chart. And that'll be based on the information. So from 0 to 100 meters, we might have a crosswind that's one velocity, and we'll calculate out what is the delta z that gives us our deflection when we get to the end of the 100 meters. And then we're going to go to maybe from 100 to 300 meters, we've got different wind conditions, and we can calculate out over that distance what is the new delta z, add that into our previous, and we come up with our z sub 2, or if we want to call it z sub 300. Sometimes it's easier to use the meters there instead of the interval number. But we can calculate that and take it through time. How much more have we moved over in our deflection in each little segment, add them all together, and that'll get us our total deflection as we went downrange. Okay, So now let's talk about a constant range wind. So we're dealing with wind that is moving in the direction that we're firing, either at us or away from us. All right, and we're going to start out with some simplifying assumptions for how we do this analysis. All right, the first one, that our wind in the y and the z direction, our crosswinds, is equal to 0. All right, we're only going to be analyzing range winds. All right, we're going to assume again that our velocity of the projectile is much greater than the wind velocity. All right, and to ensure that we meet that, we even have a criteria that the ratio of the wind to the velocity in the x direction is less than 0.01. Right? So what are the effects of the range wind when we take those assumptions in? All right. So that leads us to this equation, 9.141. All right, that our velocity with respect to distance traveled, all right, that's what the tick mark means instead of a dot over top of it, plus our drag, all right, is going to be equal to our gravity divided by the velocity in the x direction. All right, so relating how fast we go up and down to how far downrange we are, and taking into account drag. All right. So that leads us to this v tilde x, all right? So just studying the x direction here, being equal to equation 9.144, all right? And that lets us calculate then our time of flight. How long is it going to take us to get to our target, all right? So if we start out with t, all right, our time of flight being equal to what is the range we have to go divided by the average velocity that we're flying, right? That's 9.157. We could rewrite that as our t tilde, all right, is equal to our range divided by our tilde velocity averaged over the distance we have to travel, which is 9.158. All right, so we're starting to bring in this wind effect. All right, and now what is our t tilde? Okay. Well, we substitute equation, the earlier equations into this and average them out, and we get equation 9.159, all right, for calculating our time of flight in the presence of our constant range wind. The t tilde is our time of flight with the wind, all right, and our t's without anything on them is our no wind time of flight. All right, so we have to know what that is in order to calculate what it will end up being once we add these drag effects in there. All right, that concludes our lecture here about how to do calculations related to winds and what crosswinds and range winds are. Have a great day and see you in class.